Over the past century, humanity has constructed an incredibly detailed understanding of our reality. We refer to it as the Standard Model, a scientific achievement that stands as one of our greatest intellectual triumphs. This framework explains the bonding of atoms, the burning mechanisms of stars, and why we remain anchored to Earth's surface through gravity. Throughout history, it has withstood more rigorous testing than any other scientific theory. According to this model, our cosmos should be uniform, predictable, and fundamentally stable. However, there's a significant complication. The actual universe appears to have other ideas. When astronomers direct their instruments toward the heavens, they continuously discover phenomena that refuse to conform to our expectations. Structures emerge that theoretically shouldn't have the time to form. Matter accelerates at velocities that defy our calculations. Energy manifests seemingly from nowhere. It's comparable to discovering an additional room in your own home that you never built. Its presence is impossible according to your blueprints, yet there it stands. These aren't minor computational discrepancies either. These represent enormous, glaring inconsistencies that suggest our grasp of reality might be fundamentally incomplete. We're encountering objects that violate the Big Bang's established chronology. We're picking up transmissions emerging from supposedly empty regions of space. We're observing constants that may not actually remain constant at all. Today, we're examining all available data comprehensively. From the peculiar cold regions in distant cosmos to the matter that seems to have vanished from our immediate cosmic neighborhood, we'll explore 50 distinct ways our universe defies our current understanding. The truth is, our reality no longer makes coherent sense. The more intensely we investigate, the more bizarre everything becomes. Let's begin with examining the cosmic map. When you observe the universe's most ancient light, specifically the cosmic microwave background, conventional wisdom suggests it should resemble the static pattern on an antiquated television set. Just random, minuscule temperature variations distributed uniformly throughout the visible sky. This expectation stems from the cosmological principle, which states the universe should appear identical in every direction you look. No privileged locations, no peculiar formations. Then we discovered what's known as the cold spot. Initially detected by the WMAP satellite and subsequently verified by the Planck satellite, this represents a massive celestial region that simply defies explanation. It exhibits significantly colder temperatures than the surrounding cosmic background, approximately 70 to 150 microkelvin below average. While this might seem insignificant, in the field of cosmology, this temperature differential represents the distinction between a gentle wave and a catastrophic tsunami. From a statistical standpoint, this anomaly shouldn't exist. The probability of a region this extensive and this frigid appearing randomly within our standard cosmological model is less than 1%. It stands out like a dark blemish on an otherwise flawless surface. Naturally, scientists pursued every possible mundane explanation. They meticulously examined the instruments for malfunctions. They investigated potential dust interference. They scrutinized every conceivable variable. The spot persisted. It's genuine and it's enormous. If this cold spot isn't an instrumental error, what could possibly explain it? The most conventional explanation involves what's called a supervoid. Picture an immense region of space, roughly 1.8 billion light-years across, situated in the constellation Eridanus. This would be an area containing far fewer galaxies, stars, and gas clouds than typical regions. Just vast, empty space stretching endlessly. The theoretical mechanism is straightforward. As light from the cosmic microwave background traverses toward us, it passes through this enormous empty region. Because there's diminished gravitational influence pulling on it, the light loses energy as it climbs out from this gravitational depression. This phenomenon is called the integrated Sachs-Wolf effect, Reduced energy translates to lower temperature readings. Problem solved, correct? Not entirely. While astronomers did locate a void in that direction, named the Eridanus supervoid, representing the largest such structure we've ever mapped, there's a critical issue. It's not sufficiently empty. Even a cavity of this magnitude can only account for approximately 10 to 20% of the temperature reduction we observe. The mathematics don't reconcile. The void exists, certainly, but it's like attempting to explain a completely shattered window using only a small pebble. The damage vastly exceeds what the identified cause could produce. So the question remains unanswered. What generated the rest of this temperature drop? This brings us to the uncomfortable theoretical possibility, one that makes serious scientists anxious because it sounds like pure science fiction. What if this cold spot doesn't originate from our universe at all? Certain theoretical physicists, like Laura Mersini-Houghton, have proposed that our universe might not represent the only bubble floating in the cosmic foam. We could be part of something called the multiverse. During the violent expansion following the Big Bang, our bubble might have collided with another one, a neighboring universe. If two universes did collide, the impact would leave permanent evidence, essentially a cosmic scar. It would push matter away from the collision point and leave behind a region with distinctly unusual properties, manifesting as a cold spot. Now, to be absolutely clear, this isn't mainstream scientific consensus. It represents a radical proposal, but the mere fact that we must seriously consider such ideas reveals just how strange this anomaly truly is. We're staring at a section of sky that absolutely refuses to fit into our understanding of reality, forcing us to question whether our reality has boundaries and whether something collided with them from outside. If the possibility of a bruise from another universe isn't sufficiently strange, let's discuss what cosmologists have actually named the axis of evil. This isn't political terminology, that's what the scientific community genuinely calls it. Remember how the universe should be random, with no inherent up or down orientation in space? Well, when scientists analyze the temperature fluctuations in the cosmic microwave background, they discovered a pattern, a distinct alignment that defies expectations. The hot and cold patches aren't randomly scattered as they should be. They appear to line up along a specific axis. The most unsettling part? This axis aligns almost perfectly with the plane of our own solar system. Consider how absolutely absurd this is. We're examining background radiation from 13 billion years ago. It has absolutely no connection to Earth. It has nothing to do with our sun. It shouldn't care about how our planets are oriented, yet the data suggests the entire universe is somehow oriented around us. Copernicus dedicated his entire life to proving we aren't the center of the universe. The axis of evil seems to be hinting that perhaps we are cosmically special after all. More likely, there's something systematically wrong with our understanding of the cosmos. Perhaps a strange topology, like a universe shaped like a torus that forces these alignments into existence. Either way, the cosmic map isn't random as it should be. It has directionality, and we don't understand why. While we're examining maps that defy explanation, let's discuss traffic patterns. In an expanding universe, everything should be moving away from everything else. It's like dots on an inflating balloon. If you look far enough out, the expansion should be the dominant force. But in 2008, a team led by Alexander Kashlinsky found something else entirely. They examined the movement of hundreds of galaxy clusters and found that they weren't just expanding outward. They were drifting in a specific direction. A massive river of galaxies stretching across billions of light years is flowing in the same direction at nearly 2 million miles per hour. They called it dark flow. This is happening independently of the cosmic expansion. It's like tossing a bunch of corks into an exploding lake and watching them all drift sideways against the current. The drift is heading toward a patch of sky between the constellations Centaurus and Hydra. And whatever is pulling them must be enormous, much larger than anything we can observe in the observable universe. But we can't see it. The flow just goes there. Part of this motion is caused by a local gravitational anomaly we call the Great Attractor. This represents a gravitational anomaly located about 250 million light-years away from us, right in the zone of avoidance. That's the part of the sky blocked by the thick dust of our own Milky Way galaxy. We can't see it directly with optical telescopes. It's hiding behind the curtain, but we can feel its gravitational influence. Our galaxy and everything around us is being dragged toward it at 600 kilometers per second. X-ray surveys have revealed massive clusters of galaxies in that region, like the Norma cluster. But here's the complication. When we add up all the mass we can see in the Great Attractor, it's not heavy enough. It accounts for maybe half of the pull. The rest is missing. We're being dragged toward a wall of dust by a gravity source we can't fully account for. It's like feeling a tug on a fishing line, but looking down into the water and seeing nothing but shadows. It gets bigger. As we look past the Great Attractor, we found out it was just a pebble. The boulder is behind it, the Shapley supercluster. This is the most massive concentration of galaxies in our nearby universe, about 650 million light-years away. It contains over 8,000 galaxies and has a mass of 10 million billion suns. We're falling toward Shapley, but even Shapley is moving. We realize that our Milky Way, the Great Attractor, and the Virgo cluster are all just suburbs of a titanic structure called Laniakea, a supercluster of galaxies that looks like flowing tendrils of light. Laniakea means immeasurable heaven in Hawaiian, and it fits perfectly. We're just a tiny speck sliding down one of its gravitational valleys, but even Laniakea is moving. The dark flow suggests that something even beyond these superstructures, something outside the edge of our observable map, is tugging on the whole web. We are small fish in a very, very big current. Let's talk about size. Limitations. Cosmologists have a rule called the end of greatness. It basically states that structures in the universe can't get too large. Once you zoom out past about 1.2 billion light-years, everything should look smooth and homogeneous. Gravity just shouldn't be able to construct things larger than that. There hasn't been enough time since the Big Bang. But apparently, gravity didn't receive that memo. In 2021, astronomers discovered the Giant Arc. It's a crescent-shaped arrangement of galaxies that stretches a staggering 3.3 billion light-years across. It covers a huge chunk of the observable sky. This thing is 3 times larger than the theoretical limit. It's like finding a human bone that's 30 feet long. Biology says it shouldn't exist. Physics says the Giant Arc shouldn't exist. But there it is, shimmering in the data from the Sloan Digital Sky Survey. Its existence challenges the cosmological principle itself. If structures this big conform, then our assumption that the universe is uniform is wrong. The map isn't just blurry, it might be fundamentally broken. Sometimes the oddity isn't about size, but about shape. Galaxies usually come in 2 flavors, spirals like us, or blobs like ellipticals. They're messy organic shapes born from gravity and collisions. Then there's Hoag's object. It looks like something a science fiction artist drew. It's a perfect symmetrical ring of blue stars surrounding a disconnected ball of yellow stars in the center. There are no spokes, no bridges connecting them, just a ring and a core floating in perfect isolation. How do you make that? The leading theory for ring galaxies requires a collision, one galaxy punching through the center of another. But collisions leave a mess, debris, tidal tails. Hoag's object is clean. It's pristine. And there's no sign of the bullet galaxy that supposedly punched through it. It sits there 600 million light-years away, looking completely artificial. We have simulations for how galaxies form, and Hoag's object barely fits into any of them. It's a beautiful 1 in a billion freak of nature, or a sign that there are ways to build galaxies that we haven't figured out yet. But Hoag's object is just a single anomaly. The problem gets worse when the strange behavior spreads across the entire sky. This is what we see with quasars. These are the bright hearts of distant galaxies powered by supermassive black holes. They blast jets of energy into space. Since galaxies are separated by billions of light-years, their orientation should be random. A black hole in one corner of the universe shouldn't care which way a black hole in another corner is pointing. They have never met. They have never communicated. Gravity is too weak to link them over such distances. But in 2014, a study using the Very Large Telescope found that quasars across distances of billions of light-years are aligned. Their rotation axes are parallel to each other. This is spooky action at a distance on a galactic scale. It suggests that these galaxies are connected by some invisible framework, maybe giant filaments of dark matter we can't see. Or maybe they were all influenced by the same conditions at the very instant of the Big Bang, retaining a memory of a time when everything was touching. It forces us to accept a difficult truth. The universe isn't a collection of isolated islands. It is a web, and the threads connecting it are invisible to us. We're looking at a puppet show, but we can't see the strings. And if we can't see the strings, do we really know who or what is pulling them? Let's talk about history, specifically the history of everything. Before we launched the James Webb Space Telescope on Christmas Day 2021, we had a pretty confident story about how the early universe grew up. The standard cosmological model, known as lambda CDM, gave us a clear, comfortable timeline. It said that after the Big Bang, the universe went through a dark age. It was a sea of neutral hydrogen gas, completely dark with no stars to light it up. Then gravity began its slow, tedious work. It pulled tiny pockets of gas together into messy, chaotic clumps. These were the first baby galaxies. They were supposed to be small, weak, and irregular. Nothing like the beautiful spirals we see today. Over billions of years, these clumps would collide, merge, and gradually build up structure in a process called hierarchical clustering. Small things becoming big things over a long time. That was the dogma. It was written in every textbook. It fit the simulations running on supercomputers. But then James Webb opened its golden hexagonal eye, and within weeks that story was on life support. The telescope looked deeper into the infrared than Hubble ever could, allowing it to peer back through the cosmic dust to a time when the universe was only 300 to 500 million years old. This is Redshift 10 and above. According to our models, this era should have been populated by those tiny, messy blobs. We expected to see the cosmic equivalent of toddlers playing with blocks. Instead, we found monsters. We found galaxies that were massive, bright, structured. They weren't messy blobs. Some of them had fully formed disks and even spiral arms. They looked like adults sitting in a nursery. One galaxy, Glass Z13, appeared to be more massive than should be possible for its age. It was shocking because there simply hadn't been enough time for gravity to do its job. In the standard model, gathering that much gas takes time. Cooling it down so it can collapse into stars takes time. Spinning it up into a disk takes time. It's like planting an acorn and coming back an hour later to find a 100-foot oak tree with deep roots and full branches. Biology says that is impossible. Physics says these galaxies are impossible. And yet there they are, staring at us from the dawn of time, mocking. Our timeline? The data is so robust that some astronomers initially thought the telescope calibration was wrong. They couldn't believe their eyes. But as the calibration was checked and rechecked, the reality sank in. The early universe wasn't a slow waking up. It was an explosion of structure that we simply cannot explain. To understand just how bad this problem is, you have to look at the cold, hard numbers. In February 2023, a team led by astronomer Ivo Labbé from Swinburne University of Technology published a paper in Nature that shook the astrophysics community to its core. They identified 6 candidate galaxies from roughly 500 to 700 million years after the Big Bang. These weren't just big, they were impossibly heavy. The team calculated their stellar mass, basically how much star stuff they contained, by analysing the light they emitted. The brighter and redder the galaxy, the more stars it has. The results were staggering. Some of these objects had masses as high as 10 billion to 100 billion times the mass of our Sun. One candidate appeared to have a stellar mass comparable to our modern Milky Way. But remember, the Milky Way took 13 billion years of eating other galaxies to get this fat. These things did it in less than 5% of that time. Here is where the math breaks down completely. If you take the standard model of cosmology, you can calculate the baryon budget of the early universe. Baryons are just normal matter, protons and neutrons. We know how much normal matter existed back then compared to dark matter. It is a fixed ratio. You can't turn more gas into stars than you actually have available in a given region. But these galaxies are so massive that if the measurements are correct, they would have had to convert nearly 100% of the available gas in their dark matter halos into stars. And they would have had to do it with perfect efficiency. Real galaxies don't do that. Star formation is a messy, violent, and incredibly inefficient process. When stars form, they blast out radiation and supernova winds that push the remaining gas away, stopping future star formation. This is called feedback. Usually, a galaxy only manages to turn about 10 to 20% of its gas into stars before the feedback shuts it down. For Labbé's galaxies to exist, they would have to be eating faster than the laws of physics allow. They are defying the cosmic limit. Essentially, they are heavier than the universe should have been able to support at that time. It's a paradox. Either our measurements of their mass are wrong, maybe the light is being contaminated by something else, like a black hole, or our understanding of how galaxies assemble is fundamentally flawed. If it's the latter, then the standard model isn't just missing a piece. It is wrong about the very beginning. If the galaxies are eating too fast, then what's lurking at their centers is even worse. We're talking about supermassive black holes. In the modern universe, these giants sit at the hearts of most galaxies, including ours. Sagittarius A star, the black hole in the middle of the Milky Way, is about 4 million times the mass of the Sun. They grow over billions of years by swallowing gas and merging with other black holes. It's a slow, gluttonous process. But we're finding them in the early universe too, and they are way too big. Take the quasar J 313 1806, discovered in 2021. We see it as it existed just 670 million years after the Big Bang. At its core is a supermassive black hole weighing 1.6 billion times the mass of the Sun. Think about that number, 1.6 billion. There's a strict speed limit for how fast a black hole can feed. It's called the Eddington limit. Here's how it works. As gas falls into a black hole, it heats up due to friction and glows incredibly bright. This light exerts pressure, radiation pressure, pushing outward against the infalling gas. If a black hole tries to eat too fast, the light it creates pushes the food away, choking off the meal. It's like trying to drink from a fire hose. The pressure pushes you back. Based on this limit, a black hole starting from a standard stellar seed, say the remnant of a massive star weighing 10 or 20 times the mass of the Sun, would take almost 1 billion years of non-stop maximum speed eating to to grow to the size we see in J0313. But the universe wasn't even 1 billion years old yet. The math simply does not allow it. Even if the black hole ate at the Eddington limit every single second of its life, which is unrealistic because food runs out, it still wouldn't be big enough. So how did it get so big? It's mathematically impossible to get there from a single star in the time available. This means one of two things. Either the Eddington limit can be broken, which would require some exotic unknown physics like super-Eddington accretion where magnetic fields somehow trap the gas. Or these black holes didn't start as stars. They started as something else, something massive, something that skipped the baby phase entirely. And that possibility scares physicists because it implies a violent mechanism in the early universe we have never seen. This brings us to one of the most terrifying and fascinating theories in cosmology: direct collapse black holes. This is the leading attempt to fix the timeline, but it requires conditions so extreme they sound like fiction. Usually, to make a black hole, you need a star. A massive star lives its life, burns through its hydrogen fuel, fuses heavier elements, and eventually runs out of energy. Gravity wins. The core collapses and you get a black hole. But this process is limited by the size of the star. The direct collapse theory suggests that in the strange hot dense environment of the early universe, you could skip the star part entirely. Imagine a gigantic cloud of pristine gas, hydrogen and helium, floating in the dark. This cloud is millions of times the mass of the Sun. Normally, this cloud would cool down, fragment, and break into thousands of smaller pieces, forming a cluster of regular stars. That's how physics usually works. Cooling leads to fragmentation. But what if the gas couldn't cool down? What if it stayed hot? This could happen if the cloud was being blasted by intense ultraviolet radiation from a nearby galaxy. This radiation would destroy the molecules needed for cooling, keeping the gas hot. If the gas stays hot, it doesn't fragment. Instead, gravity pulls the entire massive cloud inward as a single unit. Without the heat of nuclear fusion to push back, the cloud would just keep crushing down, getting smaller and denser until, snap, it punches a hole in space-time. Instead of a black hole 10 times the mass of the Sun, you would instantly get one that is 10,000 or even 100,000 times the mass of the Sun. A heavy seed. From there, it has a massive head start. It can merge and eat its way to 1 billion solar masses in record time, explaining the monsters we see with James Webb. It sounds like a neat solution, but it creates new problems. The conditions required for direct collapse, pristine gas, plus a nearby bright galaxy to sterilize it, are incredibly rare. Simulations show it shouldn't happen often enough to explain all the giant black holes we see. And yet, because we see these monsters, something like this must have happened. The universe found a cheat code. It built giants before it built stars. And if that's true, then the early cosmos wasn't a quiet nursery. It was a factory of monsters, collapsing entire clouds of potential stars into darkness in a single stroke. While we're questioning the timeline of giants, let's look at something smaller but equally baffling: dust. Cosmic dust might sound boring. It's just soot, basically, made of silicon, carbon, and aluminum. But it's the key to understanding the age of things. It's the cosmic clock. Here's why. The Big Bang didn't make dust. It only made hydrogen, helium, and a tiny pinch of lithium. Heavy elements, which astronomers call metals, are forged exclusively inside the bellies of dying stars. A star has to be born, live out its life for millions or billions of years, fuse atoms in its core, and then explode as a supernova to scatter that dust into space. Then that dust has to cool, clump together, and grow. It's a multi-generational process. You need grandmothers and great-grandmothers of stars to live and die to create enough dust to be visible. So when we look at a galaxy like A2744 YD4, located 13.2 billion light-years away, meaning we're seeing it just 600 million years after the Big Bang, we expect it to be clean. It should be a primitive object made of pure gas. But it isn't. When the ALMA telescope, the Atacama Large Millimeter Array in Chile, looked at it, it picked up the thermal glow of huge amounts of dust. We're talking about 6 million solar masses of dust. This is a crime scene where the body is found before the murder weapon was even manufactured. How can a galaxy so young be so polluted? Even if the first stars were massive and burned out quickly, so-called population 3 stars, it's hard to explain how they produce this much material so fast. Some models suggest that supernovae actually destroy dust as fast as they make it, blasting the grains apart with shock waves. So the dust shouldn't survive the very explosions that create it. So where did it come from? Some theorists suggest that maybe quasars contribute to dust formation, or the dust grains grow in the interstellar medium much faster than we think. But neither explanation fully fits the data. The existence of this dusty galaxy implies that the early universe was chemically mature long before it had any right to be. It suggests that star formation started earlier or proceeded faster than our models allow. We're looking at a teenager that already has wrinkles and grey hair. It just doesn't fit the birth certificate. If finding dust in a baby universe is confusing, let's try something even harder to swallow. Imagine meeting someone who claims to be older than their own mother. It sounds ridiculous, right? Biology doesn't work that way. Cause must come before effect. Parents must come before children. But in astronomy, we have a star that claims exactly that. Its catalogue name is HD WIME 40283, but everyone calls it the Methusela star. It's a subgiant star located just 200 light-years away from Earth in the constellation Libra. It's moving incredibly fast through our galaxy, suggesting it isn't a local. It was likely born in a dwarf galaxy that the Milky Way ate a long time ago. But its speed isn't the problem, its age is. Astronomers have been studying this star for over a century. By analysing its composition, specifically how little iron it has, we can estimate when it formed. The less iron, the older the star, because early stars formed before the universe was polluted with heavy metals. The Methusela star has almost no iron. It's practically pure hydrogen and helium. When scientists crunched the numbers in 2013 using the Hubble Space Telescope, they got an age of 14.5 billion years. Now pause for a second. The universe, according to our best measurements from the Planck satellite, is 13.8 billion years old. So how can a star be older than the universe itself? It's the ultimate paradox, like finding a Roman coin dated 500 BC inside a dinosaur fossil. It shouldn't happen. Scientists have scrambled to fix this. They refined the models, looked at oxygen levels, and adjusted the error bars. They managed to pull the star's age down to about 14.3 billion years, with an uncertainty of 800 million years. If you push the math to the absolute limit, taking the youngest possible age for the star and the oldest possible age for the universe, they just barely overlap. But it's uncomfortable. It's a statistical squeeze. The fact that we have a star sitting right on the edge of the impossible suggests that either our understanding of stellar evolution is slightly off, or the universe is older than we think. Speaking of ingredients that don't add up, let's talk about lithium. If you baked a cake and the recipe called for 3 cups of sugar, but you only tasted 1, you would know something went wrong in the kitchen. Cosmologists have a very precise recipe for the Big Bang. It's called Big Bang nucleosynthesis. It calculates exactly how much hydrogen, helium, and lithium should have been cooked up in the first few minutes of the universe. The predictions for hydrogen and helium are spot on. They match what we see in the oldest gas clouds almost perfectly. It's one of the greatest triumphs of modern physics. But then there's lithium-7. According to the theory, we should see a specific amount of lithium in the oldest stars. But when astronomers measure it by looking at the Spite Plateau, a baseline of lithium in ancient stars, they find only about 1/3 of what the model predicts. Where did the rest go? Did the universe eat it? This is known as the cosmological lithium problem. And it's not a small error. It's a discrepancy of 300 to 400%. We've tried to explain it. Maybe our telescopes are missing that lithium. Unlikely. The spectral lines are clear. Maybe the stars destroy lithium in their cores. We modelled that, and while stars do burn lithium, they don't burn enough to explain this huge gap. Some physicists have suggested that maybe we need new physics. Perhaps unknown particles like axions or decaying dark matter interfered with the nuclear reactions in the first few minutes of time, destroying the lithium before it could settle. If that's true, then the lithium problem isn't just a missing ingredient, it's a fossil record of a ghost particle we haven't discovered yet. But for now, the recipe for the universe is missing a key component, and we have no idea who stole it. If missing atoms aren't big enough for you, how about missing galaxies? Our standard model of cosmology relies heavily on cold dark matter. This invisible stuff provides the gravity that holds galaxies together. We run massive computer simulations like the Millennium simulation to see how dark matter behaves over billions of years. These simulations predict that every large galaxy like our Milky Way should be surrounded by a swarm of smaller clumps of dark matter. Hundreds, maybe thousands of them. These clumps should attract gas and form tiny satellite galaxies. The model says the Milky Way should be buzzing with them like bees around a hive. So astronomers went out to count them, and they found about 50. Wait, the computer says thousands. The sky says 50. Where are the rest? This is the missing satellites problem. It's a massive embarrassment for the dark matter theory. Now you might ask, could they be there but just invisible? Maybe they're dark galaxies, clumps of dark matter that failed to catch enough gas to make stars. If that's true, then our galaxy is surrounded by thousands of invisible ghosts right now, silent dark halos passing through us without lighting up. Or maybe our theory of dark matter is wrong. Maybe dark matter isn't cold, slow-moving, but warm. Warm dark matter moves faster, which would smooth out the small clumps and prevent these tiny satellites from forming in the first place. That would fix the count. But changing dark matter from cold to warm messes up other things, like the structure of the cosmic web. It's a trade-off. We're stuck between seeing too few galaxies and breaking the physics that explains the big ones. So is the Milky Way lonely, or is it haunted by invisible neighbours? There's another chapter in the universe's history book that seems to have some pages torn out. It's called the epoch of reionization. Here's the setup. After the Big Bang, the universe cooled down and filled with neutral hydrogen gas. It was a fog, an opaque dark fog that blocked light. For hundreds of millions of years, the universe was effectively dark. Then something happened. The first stars and quasars turned on. Their ultraviolet light blasted the hydrogen atoms, stripping away their electrons, ionizing them. This cleared the fog and made the universe transparent, allowing us to see distant galaxies today. We know this happened. We can see the before, the cosmic background, and the after, the clear sky. But we can't get the timeline to work. When we look at distant quasars, we see something called the Gunn-Peterson trough, a signature that tells us when the fog cleared. It suggests reionization ended around 1 billion years after the Big Bang. But when we count up all the galaxies and quasars that existed back then, they don't produce enough light. It's a simple energy budget problem. To clear the fog, you need X amount of UV photons. The galaxies we see only produce Y, and Y is much smaller than X. So what cleared the fog? Was there a population of massive short-lived stars that vanished without a trace? Did black holes vomit out more radiation than we think possible? Or was there some exotic source of energy like decaying dark matter particles that helped burn away the darkness? We're looking at a clear sky, but we can't find the light switch that turned it on. The universe went from dark to light, and the math says it shouldn't have been able to. Let's combine the mystery of the missing dark matter with the mystery of the early black holes. What if they're the same thing? This is the hypothesis of primordial black holes. In the 1970s, Stephen Hawking suggested that in the chaotic high-pressure moments right after the Big Bang, long before any star formed, some pockets of space might have been so dense that they just collapsed instantly. These wouldn't be stellar black holes. They could be anything. They could be microscopic, the size of a proton but with the mass of a mountain. Or they could be massive, thousands of times the mass of the Sun. If these things exist, they could solve a lot of problems at once. Why did we see giant black holes so early with James Webb? Because they were born that way in the Big Bang. They didn't need to grow. Where is the dark matter? Maybe it's not a particle. Maybe dark matter is just billions of these tiny ancient black holes floating everywhere, invisible but heavy. It's an elegant theory, but it's also terrifying. If dark matter is made of primordial black holes, it means the universe is a minefield. It means that right now there could be an invisible black hole the size of an atom passing through our solar system. If a small one hit Earth, it would pass straight through like a bullet, causing a seismic shock. If a bigger one passed by, it could destabilize. The orbit of the planets. We've looked for them. We've searched for the flashes of light they should make if they evaporate. We've watched stars to see if they twinkle as a black hole passes in front of them. We haven't found a smoking gun yet, but the LIGO Gravitational Wave Observatory has detected mergers of black holes that are unusually heavy, masses that fit the primordial profile better than the stellar one. So the question hangs there. Is the universe filled with ancient traps left over from creation? We've looked at impossible galaxies, ancient stars, and missing lithium. All of these problems point to one terrifying possibility. Our clock is broken. The standard age of the universe, 13.8 billion years, is the bedrock of modern cosmology. It's calculated based on the expansion rate, the Hubble constant, and the models of dark energy. But if you have stars older than the universe and galaxies that grew up too fast, maybe the number is just wrong. In July 2023, a physicist named Rajendra Gupta from the University of Ottawa published a paper that made headlines. He suggested that the universe might actually be 26.7 billion years old, nearly double the current estimate. How? By combining two radical ideas. One is tired light, an old theory from the 1920s that suggests light loses energy simply by traveling long distances, not just because space is expanding. The other is the idea that the physical constants of nature, like the speed of light or the strength of gravity, might evolve over time. If Gupta is right, the impossible galaxies found by James Webb suddenly make sense. They aren't impossible monsters, they just had twice as much time to grow. The Methusela star isn't a paradox. It fits comfortably in the middle of the timeline, but fixing the age breaks almost everything else. It messes up the Big Bang nucleosynthesis, our cake recipe. It changes how we interpret the cosmic microwave. Background. Most astronomers don't buy it. Tired light has been debunked for decades because it blurs distant images, which we don't see. But the fact that such a radical theory was published in a serious journal, Monthly Notices of the Royal Astronomical Society, shows how desperate the situation is. We're so backed into a corner by the data that we're willing to rewrite the age of the universe just to make the pieces fit. Let's leave the timeline and look at the neighbours, or rather the lack of them. If the universe is as old and as vast as we think it is, we shouldn't be alone. There are roughly 200 billion stars in our galaxy alone. Many have planets, some are in the habitable zone. Even if life is incredibly rare, the sheer numbers dictate that we should see something, a signal, a structure, a probe. This is the heart of the Fermi paradox. But when we point our radio telescopes at the sky, we hear nothing. The great silence. Now, silence might sound peaceful to you, but in astronomy, silence is terrifying. It's like walking into Times Square at noon on a Tuesday and finding it completely empty. No cars, no people, no noise, just wind. You wouldn't think, oh, everyone must be napping. You would think, run. The silence suggests something is wrong with our assumptions about life. Is intelligence a suicidal trait? Do civilizations destroy themselves with nuclear fire or AI the moment they get loud enough to be heard? Or is there a great filter, some inevitable catastrophe that wipes everyone out before they can spread to the stars? If the filter is behind us, like the origin of life, we're the lucky lottery winners. But if the filter is ahead of us, then the silence isn't empty. It's a graveyard, and we're just the next grave waiting to be dug. Except the silence hasn't been absolute. There was one moment, one single minute in 1977, when the universe screamed at us. It happened at the Big Ear Radio Telescope at Ohio State University. Astronomer Jerry Ayman was reviewing the printouts of data when he saw it. A massive spike in radio waves at 1420 megahertz. This frequency is important. It's the frequency of hydrogen, the most common element in the universe. If you wanted to shout hello across the galaxy in a language everyone understands, you would use this channel. It's the cosmic water cooler. The signal was loud. It was 30 times stronger than the background noise. It was narrow band, meaning it didn't look like a natural emission from a star or a pulsar. And it lasted exactly 72 seconds, precisely the amount of time the telescope could observe a single point as the Earth rotated. Ayman circled the code on the paper and wrote "wow" in the margin. It looked perfect. It looked like them. We turned the telescopes back to that spot in the constellation Sagittarius immediately. We listened for days, years, decades. We never heard a whisper again. Was it a secret military satellite? Unlikely. The frequency is protected for astronomy. Was it a comet passing through the beam? A study in 2017 suggested comets were in the area, surrounded by hydrogen clouds. But other astronomers argue that comets don't emit radio waves that strong. To this day, the wow signal remains the only time the phone rang, and whoever was on the other end hung up before we could answer. While the wow signal was a gentle hello, fast radio bursts are a scream of rage. Imagine the energy the sun produces in 3 days. Now compress all of that power into a single millisecond. That's an FRB, a blast of radio waves so intense it can be seen from billions of light years away. We first found them in 2007, buried in archival data. At first we thought they were glitches, maybe a microwave oven in the observatory break room, which actually happened once, but then we found them coming from outside the galaxy. The weirdest part? Some of them repeat. FRB 12102, located in a dwarf galaxy, 3 billion light-years away, fires off bursts like a machine gun. Sometimes silence, sometimes 10 blasts in an hour. Another one, FRB 180916, has a cycle. It fires for 4 days, then stops for 12, like clockwork. What causes this? A magnetar, a neutron star with a terrifying magnetic field maybe. But standard magnetars burn out their energy too fast to explain the repeaters. Some physicists, like Avi Loeb from Harvard, have even suggested cautiously that they could be artificial. Imagine a giant light sail pushed by a planet-sized laser beam to near light speed. The leakage from that beam would look a lot like an FRB to a distant observer. It's a wild idea, but nature rarely makes things that turn on and off on a 16-day work schedule. Whether it's a star having a seizure or an engine warming up, FRBs prove that the deep universe is far more active and violent than we thought. If you want something that looks even more like an alien engine, look at KIC 8462852, Tabby's star. Usually when a planet passes in front of a star, the light dips by maybe 1%. It's a tiny, regular blip. Tick-tock, tick-tock. Tabby's star doesn't tick, it crashes. In the Kepler telescope data, astronomers saw the light from this star plummet by 15%, then 22%. These dips weren't regular, they were chaotic, lasting for days or weeks. And 22% is huge. A planet the size of Jupiter would only block 1%. To block 22%, you would need something half the width of the star itself. What is that big? A swarm of comets, maybe. But you would need hundreds of thousands of giant comets all perfectly aligned, which is statistically absurd. A shattered planet? There's no infrared excess heat that you would expect from dusty debris. This led to the Dyson swarm hypothesis, the idea that an advanced civilization is building a megastructure around the star to harvest its energy, and we're seeing the shadows of the solar panels under construction. Of course, further studies pointed to dust, but not normal dust. Fine-grained dust that blocks blue light more than red light. But where did it come from? Why is it disappearing? The star itself has been fading over the last century, which comets can't explain. Even if it's natural, Tabby's star is behaving like no other star in the galaxy. It's blinking at us, and we still don't know the code. If looking for life is disappointing, looking at where life isn't is downright terrifying. Let's talk about emptiness, real crushing emptiness. We know that the universe isn't perfectly smooth. It's a web. Galaxies cluster together in long filaments like threads of a spider web. And between those threads are gaps called voids. Most voids are relatively small, maybe a few million light-years across. They're just the quiet backyards of the cosmos. But then in 1981, astronomer Robert Kirshner and his team discovered something that shouldn't exist. They were mapping galaxy redshifts in the direction of the constellation Boötes, the herdsman, when they hit nothing. They found a sphere of space so vast it boggles the mind, the Boötes void. It's nearly 330 million light-years in diameter. To give you a sense of scale, our entire Milky Way is only 100,000 light-years across. You could fit 3,000 Milky Ways side by side inside this hole and still have room for dessert. Statistically, a region this size should contain at least 10,000 galaxies. We found 60 in a space meant for 10,000. This is 0.6% of the expected density. It's so empty that astronomer Gregory Aldering once said, "If the Milky Way had been in the center of the Boötes void, we wouldn't have known there were other galaxies until the 1960s. Think about that. We would have thought we were the only island in an infinite ocean of blackness. Why is it so empty? The standard theory is that smaller voids merge together over billions of years, like soap bubbles popping into a larger one. But simulations show that to get a void this big, you would need more time than the universe has existed since the Big Bang. It's too perfect of a sphere. Some speculative theories suggest it could be an expanding bubble of dark energy. Or, if you want to get really science fiction, the site of a war between Type 3 civilizations that consumed or destroyed the galaxies in that region. Of course, that's just imagination talking. But when you stare into a hole that takes up 0.27% of the entire observable universe and find nothing looking back, your imagination tends to run wild. The emptiness of the Boötes void leads us back to a darker interpretation of the Fermi paradox. Why is the universe so quiet? Why do we see huge gaps and no signals? Maybe the silence isn't because no one is there. Maybe it's because everyone who is there is smart enough to shut up. This is the dark forest hypothesis, popularized by science fiction author Liu Cixin, but based on very real game theory principles like the prisoner's dilemma. The logic goes like this: all life wants to survive. Resources in the universe are finite. Therefore, any other intelligent civilization is a potential threat. You cannot know if they're friendly or hostile. You cannot know if they will attack you first out of fear that you will attack them. In this scenario, the safest rational move for any advanced civilization is to destroy any other civilization the moment it's detected, before they can develop technology to hurt you. Strike first, strike hard. If this is true, the universe is like a dark forest at night. It's quiet not because it's empty, but because it's full of hunters. Every civilization is a silent hunter stalking through the trees, trying not to break a twig. If they make a noise, like sending a radio signal or building a Dyson sphere, they reveal their location, and then they're eliminated. This would explain the Great Silence. It explains why we don't see megastructures. It explains why the wow signal appeared once and vanished. Maybe it was a mistake or a dying scream. And it makes our own behavior, broadcasting messages like, "Hello, here we are, please come visit," look incredibly reckless, like a child lighting a flare in the middle of a battlefield. We're shouting into the dark, assuming there are friends out there. The dark forest theory suggests that the only thing listening is a predator. Okay, let's assume the aliens aren't hiding in the dark. Let's assume they're expanding, building, and consuming energy like us. If a civilization gets advanced enough, it becomes a Type 3 on the Kardashev scale. This means it controls the energy of its entire galaxy. You can't hide a galactic empire. Thermodynamics forbids it. If you build a Dyson swarm around a star to capture its energy, you use that energy to run your computers or habitats. But no machine is 100% efficient. The laws of physics say that waste heat must be radiated away. This heat would show up as excess infrared radiation. A galaxy full of Dyson spheres would look dim in visible light because the stars are covered, but would glow brightly in the infrared spectrum. So we went looking for them. In 2015, a team at Penn State University launched the G-HAT survey, glimpsing heat from alien technologies. They used data from the WISE satellite to scan 100,000 galaxies for this specific infrared signature. They found 0. Out of 100,000 galaxies, not a single one showed the clear signs of a Type 3 civilization. No one is harvesting their galaxy. This is a massive blow to our hopes or fears of ubiquitous superintelligence. It forces us to ask, is Type 3 impossible? Is there a physical limit to how much a civilization can grow? Maybe interstellar travel is just too hard. Maybe the speed of light is a cage that no one can break. Or maybe civilizations evolve into something we can't see. Maybe they upload themselves into black holes or dark matter, leaving the physical stars behind. But the data is clear. The Star Wars version of a galactic empire with ships and stations everywhere simply doesn't exist in our corner of the universe. The stars are burning free, untouched by intelligent hands. If the empires aren't out there, maybe we're looking in the wrong places. We've spent decades obsessed with the Goldilocks zone, the region around a star where liquid water can exist on the surface of a planet. Earth is our template. We look for Earth 2.0, but our own solar system is telling us that surface life might be the exception, not the rule. Look at Enceladus, the tiny moon of Saturn. It's a frozen ball of ice reflecting almost all the sunlight that hits it. On the surface, it's dead, a vacuum-sealed wasteland. But in 2005, the Cassini spacecraft saw something incredible, geysers erupting from the South Pole. Enceladus has a global ocean of liquid water buried under miles of ice. Gravity from Saturn stretches and squeezes the moon, creating heat that keeps the water liquid. Cassini flew through those plumes and tasted them. It found salt, it found organic molecules, it found the chemical ingredients for life. And Enceladus isn't alone. Europa, Ganymede, Callisto, Titan, maybe even Pluto, they all might have subsurface oceans. What if this is the norm? What if 99% of life in the universe lives deep underwater under miles of protective ice crust? They would be safe from radiation, safe from asteroid impacts, but they would also be blind. An intelligent civilization evolving in a subsurface ocean might never see the stars. They would think the universe is just water and rock. They would never develop astronomy. They would never build radio telescopes because radio waves don't travel well through water. They could be brilliant, philosophically advanced, and teeming with life, but completely cut off from the cosmos. The universe could be full of chatter, but it's all locked away under the ice, muffled by miles of frozen silence. This brings us to the most chilling statistical argument of all, the Great Filter. The concept was proposed by economist Robin Hanson. It starts with a simple observation: dead matter, atoms, eventually evolves into expanding star-faring life. We know this is possible because we're doing it, but we see zero evidence of anyone else doing it. This means that somewhere along the path from dead rock to galactic empire, there's a step that's almost impossible to take: a wall, a filter. The question that keeps astrobiologists up at night is, where is the filter? There are two possibilities. Possibility one, the filter is behind us. Maybe the origin of life, abiogenesis, is incredibly rare. Maybe getting from single cells to complex cells, eukaryotes, is a 1 in a trillion fluke. If this is true, we're the winners. We've already passed the hardest test. We're lonely, but we're special. Possibility 2, the filter is ahead of us. This is the nightmare scenario. It means that life evolves easily, intelligence evolves easily, but something inevitably kills civilizations before they can leave their home planet. Maybe it's nuclear war. Maybe it's engineered pandemics. Maybe it's unchecked climate change. Or maybe it's something we haven't even invented yet, like artificial intelligence that decides biology is obsolete. If the filter is ahead, then the silence of the universe isn't empty space. It's a warning. It means that every civilization that reached our level of technology hit a wall and died. The fact that we don't see anyone else means no one makes it past this point. We're like a turkey being fed every day, thinking life is great, unaware that Thanksgiving, the filter, is coming. Every day we survive without finding aliens actually increases the probability that the filter is still waiting for us. Finding simple bacteria on Mars would be good news. Finding ruins of an ancient city on Mars would be the worst news in human history, because it would mean they got this far and died. And we're next. While we argue about invisible civilizations and dark forests, in October 2017, something actually showed up on our doorstep. The Pan-STARRS telescope in Hawaii spotted a faint, fast-moving object tumbling through our solar system. At first, we thought it was a comet, then an asteroid. But as we tracked its orbit, we realized it wasn't from here. It had come from interstellar space, diving into our system from the direction of Vega, swinging past the Sun at nearly 200,000 miles per hour and shooting back out into the dark. We named it Oumuamua, Hawaiian for scout or first messenger from afar. And the more we looked at the data, the weirder it got. First, the shape. The light curve suggested it was incredibly elongated, like a cigar or a pancake, at least 10 times longer than it was wide. We've never seen a natural space rock with those dimensions. Asteroids are usually potato-shaped chunks. This looked engineered. But the real smoking gun was its movement. As Oumuamua left the solar system, it accelerated. Now comets do this. When a comet gets close to the Sun, the ice on its surface warms up and shoots out jets of gas, acting like tiny thrusters. This outgassing gives comets a little non-gravitational push. But here's the problem. Oumuamua had no tail, no gas, no dust coma. The Spitzer Space Telescope looked for heat from any outgassing and saw absolutely nothing. So you have a heavy cigar-shaped object accelerating without any visible propulsion. This led Avi Loeb, the chair of Harvard's astronomy department, to propose a controversial hypothesis. What if it was a light sail, a piece of defunct alien technology pushed by the pressure of sunlight? The mainstream scientific community pushed back hard. They proposed complex theories. Maybe it was a hydrogen iceberg that evaporated invisibly, though hydrogen ice is incredibly hard to form, or a nitrogen fragment from an exploded Pluto-like planet, or a dust bunny made of ultralight fractals. But every natural explanation has a hole in it. Hydrogen ice would have evaporated long before it reached us. Nitrogen fragments are statistically rare. The light sail theory, while radical, actually fits the data of the acceleration perfectly. Whether it was a rock or a wreck, Oumuamua proved one thing: we are not isolated. Stuff from out there is coming in here. And if one object passed through, how many millions did we miss because we weren't looking? It was a wake-up call. The doorbell rang, and by the time we got to the door, the visitor was already walking away down the street. Let's step back from the objects and look at the rules of the game itself. This is the mystery that bothers physicists more than any black hole or alien signal. It's the mystery of fine-tuning. If you look at the fundamental constants of nature, the numbers that define our reality, they seem suspiciously perfect for life. Take the strong nuclear force, which holds atomic nuclei together. If it were just 2% stronger, hydrogen would fuse into helium instantly after the Big Bang. There would be no hydrogen left to make water, no long-burning stars like our Sun. The universe would have burned out in a flash. If it were 2% weaker, protons and neutrons wouldn't stick together at all. No atoms, just a soup of particles. Take the cosmological constant, dark energy. Its value is incredibly small, 0 point followed by 120 zeros, and then a 1. If it was slightly larger, the universe would have ripped itself apart before galaxies could form. If it were slightly smaller, the universe would have collapsed back into a crunch within seconds. It's like walking into a room and finding a pencil balanced perfectly on its tip. It's theoretically possible, but statistically it shouldn't happen. We call this the anthropic principle. The idea is that we observe these values because if they were different, we wouldn't be here to observe them. It's a selection bias. But that feels unsatisfying. It feels like saying, I won the lottery because if I didn't win, I wouldn't be holding the check. It doesn't explain why we won. This leads to two conclusions, both of which are mind-bending. One, there is a multiverse. There are infinite universes with random constants. Most are dead, empty wastelands. We just happen to live in one of the few habitable bubbles because obviously we can't live in the dead ones. 2, the universe was designed. Simulation theory or some underlying creative principle set the dials exactly where they needed to be. Science hates the design answer because it sounds like religion. But the multiverse answer requires an infinite number of unobservable universes just to explain this one. It's a choice between an infinite lottery or a rigged game. And right now, we can't tell which one we're playing. Now we enter the territory where the actual machinery of physics starts to grind gears. If you thought the mysteries so far were just things we haven't found yet, get ready for things that prove we're wrong. The biggest crisis in modern cosmology is called the Hubble tension. It's a simple question. How fast is the universe expanding? We have two main ways to measure the speed, known as the Hubble constant. Method 1. The early universe. We look at the cosmic microwave background with the Planck satellite. We measure the physics of the infant universe, put those numbers into our best model, lambda CDM, and fast forward 13 billion years to predict how fast we should be expanding today. The answer comes out to 67 kilometers per second per megaparsec. It's a precise, clean number derived from fundamental physics. Method 2. The late universe. We look at the actual stars around us. We use standard candles, pulsing Cepheid stars, and exploding type Ia supernovae to measure distances directly. It's like using a tape measure. We see how fast galaxies are moving away from us right now. The answer comes out to 73 or 74 kilometers per second per megaparsec. 67 versus 74. Those numbers don't match and the error bars don't overlap. This is a 5 sigma discrepancy, which in physics means this is not a fluke. The chance of this being a statistical accident is 1 in 3.5 million. It's like measuring your height. You measure it with a ruler and get 6 feet. Your doctor calculates it based on your bone density and gets 5'8". Both measurements seem perfect. Both methods are sound, but you can't be both heights at once. Someone is wrong. For years, astronomers thought it was the instruments. Maybe Planck had a glitch? No. Other CMB experiments confirmed it. Maybe the Cepheids are dusty? No. Hubble and now James Webb have remeasured them with insane precision, and the tension is still there. In fact, it's getting worse. This implies something terrifying. Our model of the universe is missing a gear. The prediction from the early universe fails to match the reality of the late universe. This means something happened in between that we don't understand. Did dark energy change over time? Is there a new type of neutrino? Does gravity behave differently on cosmic scales? The Hubble tension isn't just a debate about numbers, it's a sign that the standard model, our masterpiece, is broken. Let's dig deeper into why the Hubble tension is so stubborn. Maybe the tape measure is broken. This is what the early universe team argues. They say, look, Cepheid variables are tricky. They live in crowded star clusters. Maybe you're blending their light with other stars. To fix this, astronomers developed a completely different tape measure, the tip of the red giant branch. Red. Giant stars reach a very specific peak brightness before they ignite helium in their cores. It's a standard physical limit, like a light bulb that pops at exactly 100 watts because it's based on clear nuclear physics. It should be cleaner than Cepheids. So Wendy Friedman and her team used TRGB to measure the expansion. Everyone held their breath. If TRGB gave 67, the early universe team wins. If it gave 74, the late universe team wins. The answer came back 69.8. It landed right in the middle. It didn't solve the tension. It complicated it. Now we have 3 numbers. The early universe says 67. The supernovae say 74. The red giants say 70. This is a mess. It suggests that every method has systematic errors we don't understand, or that the universe is even more complex than a simple speeding up curve. Then James Webb stepped in to settle the Cepheid argument. In late 2023, it looked at the same stars. Hubble used, but with sharper vision to separate them from the crowd. The hope was that the 74 number would drop down to 67 once the noise was cleared. It didn't happen. The Webb data confirmed the Hubble data. The number stayed high. The tension is real. The tape measure is accurate, which means the prediction is wrong. The universe is expanding faster than physics says it should. It's running away from our mathematics. So if the measurements are right, how do we fix the model? The leading contender is a desperate idea called early dark energy. We usually think of dark energy as the force that's pushing the universe apart today. It turned on about 5 billion years ago. Before that, gravity was winning. But to bridge the gap between 67 and 74, some physicists suggest that maybe there was a second burst of dark energy right at the beginning, a brief flash of anti-gravity that happened just before the cosmic microwave background was released. Imagine the universe expanding. Suddenly, a new field turns on, kicks the expansion into overdrive for a few 100,000 years, and then vanishes without a trace. This extra kick would change the size of the sound horizon in the early universe, which would change our calibration for the CMB. If you plug this early dark energy into the equations, the predicted value of 67 jumps up to about 72. It fits. It solves the tension. But it feels like a cheat. It feels like adding a fudge factor. Why would a mysterious energy field turn on, push the universe, and then turn off exactly when we needed it to? There's no evidence for this field in particle physics. It's a mathematical patch, like using duct tape to fix a cracking dam. And even with early dark energy, other problems pop up. It makes the S8 tension, another crisis about how clumpy matter is, even worse. It's a game of whack-a-mole. You fix the expansion rate and you break the structure of galaxies. You fix the galaxies and you break the age of the universe. This tells us that we aren't just missing a variable, we're missing a fundamental concept. The machine of the universe has parts we haven't identified, and right now, smoke is coming out of the engine. If the expansion of the universe is confusing, let's look at something that should be rock solid, the constants of nature. Take a number called alpha, the fine structure constant. It's roughly 1 over 137. This number controls the strength of the electromagnetic force. It dictates how electrons cling to atoms, how light interacts with matter, and ultimately how chemistry works. It's one of the pillars of reality. If alpha were slightly different, stars wouldn't burn the same way, and carbon-based life might be impossible. Standard physics assumes that alpha is the same everywhere, on Earth, on Mars, in the Andromeda Galaxy, and at the edge of the visible universe. It's a constant, right? Well, maybe not. In the late 90s, a team led by John Webb from the University of New South Wales started analysing the light from distant quasars. As this light travels billions of years to reach us, it passes through gas clouds. The atoms in those clouds absorb specific wavelengths, creating a barcode of dark lines in the spectrum. The spacing of those lines depends entirely on alpha. By measuring the spacing, you can measure the strength of electromagnetism billions of years ago. John Webb's team found something impossible. The alpha in one direction of the sky was slightly smaller than on Earth. In the opposite direction, it was slightly larger. It looked like a dipole, a gradient across the entire universe. The difference was tiny, just a few parts per million, but statistically significant. It suggested that the laws of physics aren't universal. They're local, like how the temperature changes depending on where you are in a room. Maybe the strength of electromagnetism changes depending on where you are, in the cosmos. If this is true, it's devastating for the Standard Model. It destroys the equivalence principle, the heart of Einstein's relativity. It means there is a preferred direction in the universe. Hello again, axis of evil. Critics have attacked the data for 20 years, blaming telescope calibration. But newer studies using entirely different telescopes have found hints of the same pattern. If alpha isn't constant, then constant is just a word we use to comfort ourselves. Reality might be fluid. While we question constants, let's revisit our old friend, dark matter. We treat it as an essential ingredient. You can't build a galaxy without dark matter. That's the rule. The visible stars don't have enough gravity to hold themselves together. They would fly apart without the invisible glue of dark matter. But in 2018, astronomers found a galaxy that forgot the glue. It's called NGC 1052 DF2, or just DF2? It's an ultra-diffuse galaxy looking like a ghostly smudge of stars. When astronomers measured how fast the star clusters inside it were moving, they were shocked. The stars were moving slowly, lazily. Their speed matched the gravity of the visible stars exactly. There was no room for dark matter in the equation. If there was any hidden mass, the stars would be zipping around much faster. The calculated ratio of dark matter to normal matter was basically 0. This broke everyone's brain for two opposing reasons. Reason 1, it challenges galaxy formation. How do you gather gas and stars into a clump without a dark matter well to pull them in? It's like building a house without a frame. Reason 2, ironically, it killed the alternative theories to dark matter. Theories like MOND, modified Newtonian dynamics, argue that dark matter doesn't exist. Gravity just works differently at large scales. But if gravity works differently, it should work differently everywhere. Every diffuse galaxy should show the MOND effect. The fact that DF2 doesn't show it implies that dark matter is a physical substance, stuff that can be separated from a galaxy rather than a universal law of gravity. So DF2 proved dark matter is real by not having any, but it also proved that our models of how galaxies form are incomplete because we have no idea how to make a galaxy that's naked. And then we found another one, DF4, so there's a whole population of ghost galaxies out there defying the rules of construction. Let's go deeper. Let's talk about why you exist at all. According to the standard model of particle physics, matter and antimatter are created in equal pairs, symmetry. If you turn energy into mass, E equals mc squared, you get one electron and one positron, one proton and one antiproton. They're mirror images. And when they meet, they annihilate. They turn back into pure energy. Poof. So in the Big Bang, which was a massive explosion of energy, the universe should have created 50% matter and 50% antimatter. As the universe cooled, these pairs should have collided, annihilated each other, and left behind nothing, just a bath of photons, light, but no stuff. But look around. There is stuff. There are stars. There's a screen in front of you. There's you. We live in a universe made almost entirely of matter. Antimatter is incredibly rare. We can make tiny amounts in particle accelerators, but we don't see anti-galaxies or anti-stars. Where did the antimatter go? This is the baryon asymmetry problem. Somehow, in the first fraction of a second, the universe favoured matter. For every billion pairs of matter and antimatter created, 1,000,000,001 particles of matter were created. The billion pairs killed each other, leaving that one lonely survivor. We are the survivors. We are the error in the math. Physicists call this CP violation, a breach in the symmetry of charge and parity. We've seen tiny examples of it in particles called kaons and B-mesons. But the effect is way too small to explain the universe we see. It's like trying to empty an ocean with a teaspoon. The math says we shouldn't be here. The fact that we are means there's a massive mechanism in the early universe, maybe related to neutrinos or the Higgs field, that we haven't discovered yet. We're the leftovers of a cosmic massacre, and we don't know why we were spared. If the universe is hiding particles from us, we might be on the verge of finding them. Not with a telescope, but with a magnet. Meet the muon. It's basically a heavy electron. It's unstable, short-lived, and acts like a tiny magnet. If you put a muon in a magnetic field, it wobbles, precesses, like a spinning top. The standard model can predict exactly how fast it should wobble. This prediction, called the G factor, is incredibly precise. It accounts for every known particle in the universe: photons, quarks, Higgs bosons, popping in and out of the vacuum and nudging the muon. It's a calculation involving thousands of diagrams and supercomputers. In 2021, the Fermilab muon G2 experiment released its latest results. They shot billions of muons around a giant magnetic ring to measure the wobble. The result? The muon is wobbling too fast. The difference is tiny, 0.00 something, but it has reached a statistical confidence of 4.2 sigma. That's tantalizingly close to the 5 sigma gold standard for discovery. Why is it wobbling too fast? Because something is pushing it, something that isn't in the standard model. It could be a Z-prime boson, it could be a leptoquark, it could be a supersymmetric partner particle, or it could be dark matter interacting with the muon. Whatever it is, it's a ghost in the machine. The muon is feeling a force we don't know about. This tiny wobble is currently the strongest evidence we have that the standard model is incomplete. The bedrock of particle physics has a crack in it, and the muon is dancing right over the edge. And finally, we arrive at the single biggest embarrassment in the history of theoretical physics, the vacuum catastrophe. We tend to think of a vacuum as empty, nothing. But quantum mechanics says that's wrong. The vacuum is alive. It's seething with virtual particles popping in and out of existence, fluctuations in the quantum fields. Since energy and mass are equivalent, this seething activity has energy. Gravity should feel this energy. It should pull on the fabric of space-time. So physicists decided to calculate how much energy is in the vacuum of space. They took quantum field theory, summed up the contributions from all the fields, and got a number, a huge number. Then they looked at the actual universe. We can measure the energy of the vacuum by looking at how fast the universe is accelerating, dark energy. The theoretical number is larger than the observed number by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. It's not just wrong, it's spectacularly, hilariously wrong. It's the worst prediction in science. If the theoretical number were true, the universe would have expanded so fast that no atoms could have ever formed or collapsed instantly. The fact that space is relatively calm means that something is cancelling out almost all of that quantum energy perfectly to 120 decimal places, but leaving just a tiny bit left over to drive the current expansion. We have no idea how this cancellation happens. Is it a coincidence? Is it a symmetry we haven't found? Or do we fundamentally misunderstand what a vacuum is? This discrepancy suggests that our two best theories, quantum mechanics, the very small, and general relativity, the very big, are violently incompatible when they try to talk about nothing. The vacuum catastrophe is a theoretical embarrassment. But we can actually see this strange energy in the lab. It's called the Casimir effect, and it's the closest thing physics has to magic. In 1948, Dutch physicist Hendrik Casimir predicted that if you took two uncharged metal plates and placed them incredibly close together in a perfect vacuum, they would move. Not because of gravity, not because of magnetism, but because of the nothingness between them. Here's the logic. The vacuum is full of virtual particles behaving like waves. Outside the plates, waves of all sizes can exist, but between the plates, the space is so tight that only small waves fit. It's like trying to play a low bass note on a tiny guitar string. It just doesn't work. Because there are fewer waves pushing from the inside than from the outside, there's a pressure difference. The empty space outside pushes harder than the empty space inside. The result? The plates are crushed together by the vacuum itself. This force is tiny but real. In 1997, Steve Lamoureux at Los Alamos National Laboratory measured it precisely. He brought a sphere and a plate to within a few micrometers of each other and detected a force of about 1/1000th of a Newton. That matches the theory perfectly. This proves that empty space has mechanical strength, it has weight. It can push things around. So if the vacuum can crush metal plates in a lab, why isn't it crushing the universe or ripping it apart? The fact that we can measure this energy on a small scale makes the vacuum catastrophe on the large scale even more baffling. We know the energy is there. We can touch it. But when we look at the stars, it's missing in action. If empty space is unstable, what about matter itself? We assume that atoms are forever. A proton is a proton is a proton. It was born in the Big Bang and it will survive until the end of time. But most grand unified theories, the theories that try to combine all the forces of nature into one, say that's wrong. They predict that protons are mortal. Eventually, every proton in the universe should break down into a positron and a pion. If this is true, then all matter is slowly evaporating. You, the Earth, the Sun, we're all made of temporary ingredients. To test this, scientists built a massive detector called Supermassive. It's a tank filled with 50,000 tons of ultra-pure water, buried 1,000 meters underground in a Japanese mine to shield it from cosmic rays. The tank is lined with 11,000 light sensors. The idea is simple. If a single proton in all that water decays, it will emit a tiny flash of light. They've been watching for decades and they've seen nothing. The proton seems to be stable for at least 10 to the power of 34 years. That's a 1 followed by 34 zeros. That's billions of times longer than the age of the universe. This sounds like good news. We aren't going to dissolve anytime soon. But for physicists, it's a disaster. It means the grand unified theories that predict proton decay are wrong. We tried to unify the forces, and the proton said no. It suggests that there's a fundamental wall between the forces of nature that we can't break down. Or perhaps the decay takes so long that we just haven't been lucky enough to catch one yet. Either way, the stability of the proton is a silence that screams that our best theories are missing something huge. And this leads us to the ultimate wall, the one we've been banging our heads against for a century, the incompatibility of quantum mechanics and general relativity. We have two rulebooks for the universe. Rulebook 1, General Relativity. It says space is smooth like a trampoline. Gravity is just the curvature of that fabric. It works perfectly for stars, galaxies, and black holes. Rulebook 2, Quantum Mechanics. It says the world is pixelated, made of discrete chunks of energy. It works perfectly for atoms and subatomic particles. Both rulebooks are verified by thousands of experiments, but they speak different languages. If you try to combine them, if you try to calculate the gravity of a single electron, the math explodes. You get infinity as an answer. Infinity is not a number. It's the equations telling you that they're broken. This crisis happens at the center of a black hole, a singularity. It's a point where a massive amount of stuff, relativity, is crushed into a tiny space, quantum. The two theories fight, and physics collapses. We simply do not know what happens there. The laws of nature stop working. We've tried to fix this with string theory, which says particles are vibrating loops. We've tried loop quantum gravity, which says space is made of tiny woven knots. But neither theory has produced a single testable prediction. We're stuck. We're using two different maps for the same territory, and the borders don't line up. Until we find a theory of quantum gravity, we don't really understand the universe. We only understand the easy parts. The core, the singularity, remains completely hidden from us. Now we enter the final chapter, the one where we question not just the objects in the universe, but the stage itself. Let's start with time. You feel time flowing. The past is gone. The future hasn't happened. The present is the only thing that's real. That's how it feels to be human. But Einstein's relativity says that feeling is a lie. In relativity, time is just another dimension, like length, width, or height. It's part of a four-dimensional structure called space-time. And just like all of space exists at once, all of time exists at once. This is called the block universe. Imagine a loaf of bread. Every slice is a moment in time. The dinosaurs are on one slice, you're on another. The death of the sun is on another. Just because you're currently conscious on your slice doesn't mean the other slices aren't there. They're all equally real. This means the past isn't gone. It's just down the road. And the future isn't unwritten. It's already there, waiting for you to experience it. This destroys the idea of free will. If the future already exists in the four-dimensional block, you're just riding a roller coaster track that's already been built. You can't change the turn that's coming up. Physicists argue about this constantly. Some say quantum mechanics reintroduces randomness and breaks the block. Others say the math of relativity is clear. Simultaneity is relative, so there's no universal now, and therefore the past and future must exist. If they're right, then the flow of time is just a trick of our biology, a hallucination to stop everything from happening at once. If you think the block universe is bad, let me introduce you to the Boltzmann brain. This is a paradox that comes from the laws of thermodynamics and entropy. Ludwig Boltzmann, a 19th century physicist, suggested that the universe could be a random fluctuation. Out of an eternal chaotic void, particles just happen to come together to form stars and galaxies. But here's the problem with probability. It's much easier to form a small simple thing by chance than a huge complex thing. It's exponentially more likely for random particles to come together and form just a human brain, complete with false memories of a past life, than it is to form an entire universe with billions of galaxies and real history. According to the math, for every one real universe, there should be trillions of lone brains floating in the void, hallucinating that they're reading a script about space mysteries. So statistically speaking, you're probably not a person sitting in a room. You're probably a Boltzmann brain floating in deep space, imagining the room, imagining the screen, and imagining me telling you this. This is not a joke. It's a serious problem in cosmology. If our theories predict that freak observers are more common than real observers, then our theories are wrong. We call this the measure problem. We have to find a reason why the universe favors big complex structures over simple lonely brains. But so far the math suggests that reality is the less likely option. It's a thought that makes you want to check if the walls of your room are solid. But of course, in a hallucination they would feel solid, wouldn't they? If the idea that you're a floating brain is too abstract, let's look for something harder, like pixels. If we're living in a simulation, a matrix-style digital reality created by a post-human civilization, there should be limitations. Every computer has a limit to its processing power. It has a resolution. It has to cut corners to save memory. So physicists have started looking for the pixels of our universe, and disturbingly, they might have found them. One clue comes from high-energy cosmic rays. These are particles traveling across the universe at nearly the speed of light. In 1966, three physicists, Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, calculated a theoretical speed limit for these particles. It's called the GZK limit. They argued that if a cosmic ray travels too fast, above 5 × 10 to the 19th electron volts, it should crash into the photons of the cosmic microwave background and lose energy. It's like trying to run through a crowd. Eventually you bump into someone and slow down. This acts like a hard cap on velocity in the universe code. It looks suspiciously like a variable constraint in a software program to prevent stack overflow. Another clue is the Planck length. This is the smallest possible unit of measurement, about 1.6 × 10 to the power of -35 meters. You cannot measure anything smaller. It is the absolute bottom, Why does the universe have a minimum resolution? Why isn't space infinitely smooth? Simulation theorists argue that the Planck length is the grid size of the simulation. It's the pixel. Then there's error-correcting code. In theoretical physics, specifically in string theory and supersymmetry, James Gates discovered mathematical structures that look identical to binary error-correcting. Codes used in modern web browsers, specifically Hamming codes. It's literally computer code embedded in the equations that describe the fabric of reality. Is this proof? No. It could be that math is just the language of nature, and computers use math, so they look similar. But the fact that the universe has hard limits on speed, resolution, and information density makes it look a lot less like a wild organic place and a lot more like a rendered environment running on a very, very powerful machine. And if that's true, the scariest question isn't how does it work, it's who is holding the off switch. Speaking of off switches, physics has identified a way the universe could end today without warning. It's called false vacuum decay, and it has to do with the Higgs boson. The Higgs field is what gives particles mass. Think of it as a surface. Everything in the universe wants to be at the lowest possible energy state, the bottom of the valley. We assume that our vacuum, the state of empty space, is at the true bottom, the true vacuum, stable, safe. But measurements of the mass of the top quark and the Higgs boson suggest that we might be wrong. We might be in a false vacuum. Imagine standing on a ledge halfway down a cliff, thinking you're at the bottom. You're stable for now, but the real bottom is 1,000 feet further down. All it would take is a tiny push to send you falling. In quantum mechanics, this push can happen spontaneously through a process called quantum tunneling. At any moment, in any random spot in the universe, a tiny bubble of true vacuum could appear. Inside this bubble, the laws of physics would be rewritten. The constants of nature would change. Chemistry would become impossible. Atoms would fall apart. And here's the bad news. This bubble would expand at the speed of light. Because it moves at light speed, you would never see it coming. There would be no warning, no flash on the horizon. 1 second you're there, the next nanosecond your atoms have dissociated, and the fundamental structure of your reality has been deleted. This bubble would eat the entire universe, converting our false vacuum into true vacuum. It's the ultimate cosmic format. Some calculations suggest the universe is metastable, meaning we're safe for billions of years. But others suggest the edge is closer than we think. We're living on a tightrope, and we don't even know how far down the drop is. It's the ultimate reminder that our existence is fragile, dependent on energy fields staying balanced on a knife's edge. If the vacuum doesn't delete us, dark energy might tear us apart. We know the universe is expanding. We know the expansion is accelerating. For a long time, we thought this just meant galaxies would drift away from each other until the sky was dark, a lonely cold death called the Big Freeze. But recent data suggests a much more violent ending, the Big Rip. This depends on a number called W, the equation of state parameter for dark energy. It measures how the density of dark energy changes as the universe expands. If W is exactly -1, the density stays constant, standard model. But if W is less than -1, say -1.1, then dark energy gets stronger over time. This is called phantom energy. If phantom energy is real, the expansion will go rogue. It won't just push galaxies apart. It will overcome gravity entirely. It will rip galaxies apart. Then it will rip solar systems apart. Planets will be flung from their stars. In the final moments, the expansion force will become stronger than the electromagnetic force holding atoms together. Stars and planets will explode. Then molecules will be shredded. Finally, in the last fraction of a second, atoms themselves will be ripped apart. even the fabric of space-time will be torn asunder. The universe ends not with a whimper, but with a violent shredding of everything that exists. Current measurements from the Planck satellite put W at about minus 1.03 with error bars. That puts us dangerously close to the phantom energy zone. We can't rule it out. So while we worry about asteroids or climate change, the universe itself might have an expiration date where the physics holding your body together simply stops working. So is the end really the end? Sir Roger Penrose, a Nobel Prize winner and one of the smartest minds in physics, says no. He believes in conformal cyclic cosmology. The idea is that the Big Bang wasn't the beginning. It was just a transition, a bounce. Penrose argues that in the very distant future, after all the stars have burned out and black holes have evaporated via Hawking radiation, the universe will contain nothing but photons, light. Here's the trick. Photons have no mass, and because they have no mass, they don't experience time or scale. To a photon, a universe that's infinitely big looks exactly the same as a universe that's infinitely small. The concept of size vanishes at this moment. Penrose says the geometry of the universe resets. The infinite cold future of one aeon becomes the hot, dense Big Bang of the next aeon. It's a beautiful poetic cycle. But Penrose claims there's evidence. He points to Hawking points, strange rings in the cosmic microwave background. He argues that these rings are the gravitational echoes of supermassive black hole collisions from the previous universe. Ghostly ripples that survived the end of the world to leave a fingerprint on our sky. Most cosmologists are skeptical. They say the rings are statistical noise. But if Penrose is right, then we're living on a graveyard. The atoms in your body might be recycled from the ashes of 1 trillion previous universes. It changes the story from Genesis to reincarnation. We're just one breath in an eternal lung, expanding and contracting forever. It makes our mysteries seem small, but it also makes our existence infinitely recurring. We've reached the edge of physics. We've talked about simulations, tears in reality, and eternal cycles. But there might be a final logical wall that stops us from ever knowing the truth. In 1931, mathematician Kurt Gödel dropped a bomb on the world of logic. He proved his incompleteness theorems. In simple terms, he proved that in any complex logical system, like mathematics, there will always be statements that are true but cannot be proven within the system. You cannot use math to prove all of math. There will always be blind spots. Why does this matter for space? Because physics is built on math. If the universe is a mathematical system, then Gödel's theorem applies to it too. This implies that a theory of everything, a single equation that explains all of reality, might be impossible. Not because we aren't smart enough, but because logic itself forbids it. There might be laws of physics that are true, but we can never prove them. There might be constants that have values for no reason we can verify. We might be trapped inside a system that's fundamentally incapable of explaining itself. This is the ultimate humility. We're trying to decode the universe using a language, math, that has built-in limits. It's like trying to draw a perfect circle using pixels. You can get close, but you'll never get it perfect. The mysteries we've listed, the cold spot, the Hubble tension, the vacuum energy, might not be puzzles waiting to be solved. They might be the Gödelian cracks in the system, the places where logic fails. And if that's true, then the feeling that nothing makes sense anymore isn't confusion. It is the correct answer. So where does that leave us? We started this journey looking for errors in the map. We found cold spots that shouldn't exist, and galaxies flowing like rivers toward unseen monsters. We looked at the timeline and found stars older than the universe and black holes that grew too fast. We looked for neighbors and found only a terrifying weaponized silence. We drilled down into the foundation of physics, and found cracks in the constants, particles behaving badly, and a vacuum energy calculation that's wrong by 120 orders of magnitude. It's tempting to look at this list of 50+ anomalies and say, well, science is broken. It's tempting to throw up our hands and say, we know nothing. But that's the wrong takeaway. The fact that we found these anomalies is the victory. 100 years ago, we didn't know enough to be confused. We thought the Milky Way was the entire universe. We thought time was constant. We thought atoms were solid balls. The confusion we feel now is a symptom of higher resolution. We're seeing the glitches because we're finally looking closely enough. However, the sheer number of these problems suggests that we're approaching a paradigm shift. Thomas Kuhn coined this term. Science doesn't move in a straight line. It stays steady for a while, accumulating anomalies that don't fit until the pressure becomes too great. Then suddenly, the old model shatters and a new one takes its place. Newtonian gravity worked perfectly until Mercury's orbit didn't fit. Then Einstein shattered it. We're in that Mercury moment right now. The Standard Model is creaking under the weight of the Hubble tension, the JWST galaxies, and the dark sector. Something is about to break. And when it does, our view of reality will change as drastically as it did when we realized the Earth wasn't flat. But there's a deeper twist, a scarier one. Throughout this entire video, we've assumed that making sense is the default state of the universe. We assume that logic, cause and effect, and math are the bedrock of reality. We assume the universe should be understandable to a primate brain that evolved to hunt antelopes on the savannah. Why? Why should the cosmos care if we understand it? The anomalies might not be errors. They might be windows into the true nature of things, a nature that's chaotic, non-local, and fundamentally alien to human logic. The quantum world already hints at this. Things can be in two places at once. Cats can be alive and dead. The weirdness isn't a bug, it's a feature. Maybe the reason we can't explain the cold spot or the axis of evil is that we're trying to force a non-linear, multi-dimensional universe into a three-dimensional linear story. We're trying to read a novel written in a language that has no alphabet. The glitches are just the moments where our translation software fails. And if that's true, then the mystery is the point. The fear we feel when we look at the great void or the false vacuum isn't just fear of the unknown. It's the vertigo of realizing that we're small and the universe is vast, and it's under no obligation to follow our rules. We live on a small rock orbiting a mediocre star in the suburbs of a standard spiral galaxy. We've built a little island of light called science to keep the dark away. And it works. It keeps the lights on and the planes flying. But every time we point a telescope into the dark, we're reminded that our island is tiny and the ocean is infinite. We've seen that the history of the universe is darker and stranger than we imagined. We've seen that our safety is an illusion maintained by fragile energy fields. We've seen that we're likely alone, or worse, hiding in a forest full of predators. The next time you look up at the night sky, don't just see the pretty lights. Look at the black space between them. That's where the dark matter is flowing. That's where the vacuum energy is seething. That's where the signals from dead civilizations might be passing through you right now. We're drifting in the dark. We don't have a map. The clock is broken. The compass is spinning. And the only thing we know for sure is that nothing makes sense anymore. And honestly, I wouldn't have it any other way. Because a universe that makes sense is a small universe. A universe that terrifies us? That's a universe worth exploring. Sleep tight. If you enjoyed this descent into madness, make sure to hit that subscribe button. It won't save you from a vacuum decay event, but it will help the algorithm. I want to know which of these mysteries keeps you up at night. Is it the dark forest, the simulation theory, or the idea that the universe is just broken? Let me know in the comments down below. And if you want to dive even deeper into the impossible, check out this playlist right here. Thanks for watching, and I'll see you in the next one. Assuming the universe is still here,